is a combination of translation plus rotation. And we ended up with the conclusion that we get very, very blurry photos because looking at the translational velocity of something that is moving in rolling motion gives you a different velocity at each point of the object. Now, we'll look a bit about the forces and the kinetic energy of rolling. And again, we'll not be discussing any new forces. But what we're going to be doing is we're going to be looking at everything we have done before with a slightly different view to accommodate for rolling forces and energies too. Now, if we take a rolling object, fixed at point P, and just look at the rotation, we should be seeing something like this, right? Like this red circle is moving. Now, of course, this doesn't really happen because we have the floor and this thing cannot go through the floor. But nevertheless, the kinetic energy content would be half I omega Nevertheless, the kinetic energy would be half I omega squared for the rotation bit. Now, this thing says IP because the rotation is about point P. Now we know for a disk at I center of mass, we know what it is, so we just add mr squared. That is fine. We end up with this. Our kinetic energy total for something that is moving in a circle. Yes, Yasin. Can you not see it? Can everyone see it? Okay, disconnect and reconnect, and hopefully you'll be able to see it. So our total kinetic energy would be the kinetic energy of rotation plus the kinetic energy of movement, translation. So literally, remember how in the previous lecture we were saying, okay, this is a rotation alone, this is translation alone. Well, we do the same thing with kinetic energy. We say, hey, look, if we just look at the rotation bit, the kinetic energy is half I omega squared, right? If I look only at the movement, it's half mv squared. Add them up together. That's our total kinetic energy. Which makes sense. You have two kinetic energies, you add them up, done deal. So, in conclusion, a rolling object has two types of kinetic energy: rotational kinetic energy and translational kinetic energy. Rotational due to its rotation about its center of mass. Translation is because due to the translation of the center of mass. That's kinetic energy. Let's look at the forces. Okay. We have a rotating tire. Please tell me at least some of you have played with rotating tires when you were kids. Putting a stick through a tire and, just rolling it around. Okay, so I'm not that old. Yeah? Good. I'm happy to hear that. You still have a chance if you haven't done so already. It's really a lot of fun. Okay. Well, except if you get your white dishtasha or your, white shoes all dirty. And then, if you're 10 or 12 years old, Moms usually aren't very happy about that. Anyway, so now while this thing is rolling, okay, we have two options. One option is it's simply rolling like this. Another option is this happens. Okay. Now بالعماني نقول عن هذا يشوح. It slips. It slides. Okay. Now the forces at action for these two are very, very different. In the second one, it rotates and then stops rotating and going straight. It's what happens when the brakes in your cars lock up, la samahallah. Now, if you have read ahead in your book, you would see that in a lot of the problems they mention rolls smoothly without sliding, rolls smoothly without sliding. And there's a very good reason for that, because the physics for with sliding and the physics for without sliding are actually very, very, very different. So let's take a look. This is something rotating, and the friction force is in the opposite direction to movement. If this thing is moving clockwise, point P is moving in this direction, so friction is in the opposite direction. In smooth rolling motion, your acceleration of the center of mass is equal to alpha r. So let's do this with an example. Say I have a ball that is rolling down the ramp. I have my friction force. I have my gravity force. Now you will notice that the gravity force is from the center of mass, while the friction force is at the touching point. Okay, this is very, very important. Okay, you have your normal force. There we go. These are our forces. F cosine, Fg cosine theta, Fg sine theta, Fn, and friction. So far, so good? Anyone has issues with any of this so far? Okay. Let's analyze the forces here. And the x-axis, F net equals ma. We have friction in one direction, mg sine theta in the other. Fs minus mg sine theta equals ma. But we also have another thing. This thing is rolling, right? So we also have the angular version of this equation. Torque net equals I alpha. Now we know that torque is R cross F. The only force that is not taking place at the center of mass is what? Is friction. All the other forces are taking place at the center of mass. So R, the distance for them, is 0. But here in this case, your friction is not at the center of mass. It's one radius away at the contact point. So my torque force is Fs, and the R, the moment arm, is my radius. Let's put it back. R of S equals I com alpha. Alpha is A over R. So I am starting to rearrange to have Fs on its own. So I have Fs equals I com A com over R squared. And I have a minus direction, because since this thing is going clockwise or anti-clockwise. I end up with this. my acceleration is a combination of g sine theta minus g sine theta over 1 plus I com over mr squared. Now this is very different than what we used to have before when we had just something sliding. When we had something sliding, we had fs minus mg sine theta equals ma, done. We know a, or a is 0, and we just solve it and we are done. But here, we have this extra bit of torque for the rolling that changes things and makes it more complicated. Any questions on this? Okay. Let's do sample problem 11.01, which arguably is quite a simple problem. A ball rolling down ramp. A uniform ball of mass m 6 kilograms and radius r rolls smoothly from rest down a ramp of angle theta equals 30 degrees. The ball descends a vertical height h equals 1.2 meters to reach the bottom of the ramp. What is its speed at the bottom? Now before, what we would do was simply say, well, height is 1.2, mgh equals half mv squared, and we would find v, right? This is what we would be doing before, without rotation. But now we have rotation, so that is not possible. That is not possible. We need to take rotation into account. We have extra terms. My initial kinetic energy plus initial potential energy is equal to my final kinetic energy plus my final potential energy. Initially, I don't have any kinetic energy, but I have my potential energy, mgh. Finally, I don't have any potential energy, but I have kinetic energy of half I com omega squared plus half mv squared. Vcom is equal to square root 10 over 7 GH. ACOM, we have calculated before. We know what Fs is. And that's that. Now, some people might say, okay, wait, stop. Vcom square root 10 over 7 GH. How did you even get to that? You skipped a few steps. Yeah. How did we end up with that Vcom? Well, at the top, we said we have mgh. At the bottom, we said we have half I com omega squared plus half mv squared. I'll keep mgh. Since this is a ball, its rotational inertia would be 2 over 5 mr squared at I com omega squared plus half mv squared. V equals R omega, which implies omega equals V over R. So mgh equals half 2 over 5 mr squared V squared over R squared plus half mv squared. Now we simplify. The m's all cancel. The 2's here cancel. The R squares cancel. And we end up with GH equals V squared over 5 plus V squared over 2. So GH equals 7 over 10 V squared which means V equals 10 over 7 GH square rooted. Okay. This is boring, so let's do a couple of PIQs to get everyone excited and to see if we have understood what we have been doing so far. If you go to today's lecture, PIQs, ready? A hollow cylinder of mass m and radius r rolls down an inclined plane. A block of mass m slides down an identical inclined plane. Complete the following statement. If both objects are released at the same time, the cylinder will reach the bottom first, the block will reach the bottom first, the block will reach the bottom with greater kinetic energy, the cylinder will reach the bottom with greater kinetic energy, or both the block and cylinder will reach at the same time. Hint, you probably don't need to do calculations for this one. Okay. Let's see how things went. Interesting. We have 23 people who said the block will reach the bottom first. We have 21 people who said the block will reach the bottom with greater kinetic energy. And we have 9 people who said the cylinder will reach the bottom first. And then we have 4 and 5 people choosing the last 2 answers. A rather interesting combination. Let's think of it without calculations. The block will change all the potential energy into kinetic energy half mv squared. So the block will have mgh equals half mv squared. M's cancel. So v is 2gh square rooted. Anything that rotates will have to share that potential energy between half mv squared and half I omega squared. So even with the least amount of half I omega squared, you would still be leeching off the half mv squared energy, which means the block will have higher velocity than the cylinder. So we know this is not possible. We know this is not possible. But we don't know which one of them will have the greater kinetic energy. Which one of them will have the bigger kinetic energy? Any ideas? Well, they will both have the same kinetic energy total because they're both getting it from the same mgh. So your total amount of energy is the same. Hence, the only possible answer is the block will reach the bottom first. Whether you have half mv squared or half mv squared plus half I omega squared, your total energy still is mgh. Yo-yos. Now that's a game that a lot of us have played. Okay. Or at least I'm hoping so. What is the physics of a yo-yo? How does it work? Well, I have my equation from before. I'm just going to keep using it over and over again because I'm too lazy to rederive it. A equals minus g sine theta 1 plus over 1 plus I over mr squared. I'm too lazy to do otherwise. What are the forces on a yo-yo? Well, on the center of mass, we have gravity acting, Fg, downwards. And we have the rope or the string that we're holding it with. And you'll notice that the string doesn't actually attach in the middle, but to the edge of the spindle. So look, you have this distance here between your center of mass and where this thing actually is. Now my theta here, my angle here is 90 degrees and sine 90 is 1. So my acceleration of my center of mass is simply going to be this without sine theta. Do you have any questions on the yo-yo? Okay, moving on. Torque revisited. Now I already told you this before, although your book didn't when we're doing it in chapter 10. I already told you this beforehand. I told you that torque is equal to R cross F. Okay, so torques that produce counterclockwise rotation, positive. Torques causing clockwise rotation, negative, as usual with anything rotating. Clockwise, negative, counterclockwise, positive. Let's do an example. Sample problem 11.02. In figure 11-11A, three forces, each of magnitude 2 newtons, act on a particle. The particle is in the xz plane at a point A, given by vector position r, where r is equal to 3 meters and theta equals 30 degrees. What is the torque about the origin due to each force? Well, let's see. Let's take the first one, F1. F1 is at 150 degrees because my r is at 30 degrees and the total is 180. So the distance between F1 and theta and the r is 150 degrees. Okay. What is the torque? Torque is R cross F, otherwise known as RF sine theta. R is 3 meters, F is 2 newtons, theta is 150, so sine 150, and we get 3 Newton meters. Okay. In which direction is this 3 Newton meters? Well, if we do our right-hand rule, like we studied in chapter 2, okay, we will have R cross F, and I will end up with it going into the page. So into the y-axis. What about this one, F2? F2 is downwards, so the angle is 90 plus 30, 120 degrees. We do the same calculation again, and we get 5.2 Newton meters. In which direction will it be this time? Can anyone try it and tell me? No, not a single person. Okay. If you do it, you will see that the answer is in the plus y-axis out of the page. Third one, same calculation, but you end up with 6 newtons. And this is a drawing of the 3 torques. Here's a question. Uh, okay. A planet in elliptical orbit about the Sun is in the position shown. With the origin located at the Sun, the vector torque on the planet is what? Okay. We have an overwhelming majority of people. Let's just wait until the results are all tallied. So we have an overwhelming majority that says the angular momentum, sorry, that the torque is 0. Okay, so it's not even close. It's 54 versus 7 and 6. And indeed, the answer is 0. Okay. So very well done, because your R and your F are both in the same direction, so your angle is 0. Your R is this way, your F is also this way, so your torque is 0. Which is why, if you don't know how to do the calculation, which is why our planets are going around the sun in elliptical orbits without going up or down. Yeah? We're not going in 3D dimension orbits around the sun. We're pretty much doing it in 2D with slightly 3D-ish. Yeah? Good. Reminder, linear momentum, P equals mv. Now, if I want to translate this to angular, like in chapter 10, we kept translating stuff from, linear to angular, linear to angular. How would this translate? What would it be? Anyone still alive here? Or am I talking to myself? No? Okay, since there's no interaction, I will simply continue without asking many more questions. It's easier for me, and it will just enable me to go through the syllabus faster. As usual, when we translate, the cousin of M is I, the cousin of V is omega. So our momentum is going to be, in translation, I omega instead of MV, and we will give it a new letter. When I have an object going in a circle, it has a momentum P equals MV in one specific direction at some angle phi. Now, if we are doing it with the moment arm, we end up only taking one component of this. We have the cosine component and we have the sine component, and we only end up taking, for the angular, just like with force and torque, we did R cross F, right? We only took the sine component of the F. Well, we only take the sine component of the MV. So MV sine theta or P sine theta, which means we end up with an angular momentum, which we give it a letter L that says MV or P R sine theta, otherwise known as R cross P. Okay, so just like torque was R cross F, angular momentum is R cross P. Okay. And it is a vector quantity, so its direction is given by the right-hand rule, as usual. You have R in one direction, on one finger, P on the other one, and your angular momentum is going to be in the direction of the cross product of that. Okay, now, you might be asking yourselves, okay, what is the point of all of this? And I will tell you as soon as we're done with this upcoming PIQs. What is the, you have all seen this angular momentum thing before, you just haven't really known that you were looking at it. Okay, so next PIQ. How does the magnitude of the angular momentum of the planet L with the origin at the sun at positions A and B compare? LA equals LB, LA is less than LB, or LA is more than LB? Okay. We have an overwhelming majority that say LA equals LB. We have a minority that say LA is more than LB, and pretty much no one or just one person said LA is less than LB. The correct answer is indeed LA equals LB. But can anyone explain to me why? Why is LA equal to LB? Come on, 59 people chose LA equals to LB. At least one of you should be able to tell me why are they the same? Same angle, okay. Torque is 0 because angular momentum is conserved. Yep. Okay, good. So you are awake after all. I just need to push you to get any answer out of you, don't I? Okay. Why did this thing stop sharing the screen? Okay. Indeed, angular momentum is a conserved quantity, okay, just like linear momentum. And what happens is, okay, what happens is L equals R cross P, which is equal to M R cross V. Yeah. Now what happens is when my R is smaller, my R is less, my V is more. And when my R is more, my V is less to conserve the quantity. Okay. All right. We have 5 more minutes left. So I'll tell you a bit, okay, about where have you seen angular momentum before. I don't want to start a new lecture yet, but I want to tell you a bit about where have you seen this before. How many of you have taken chemistry in high school?
Yes.
Okay. Do you remember something that looks like this?
Orbitals?
Yep. Do you remember these orbitals that go like this? They went like this, then like this, then like this, then like this, and so on and so forth. Remember these? What is this SPDF? Did they tell you what these SPDFs are? They called them orbitals, but what's the difference between S and P and D and F? Shape of it. So they told you that, the S orbital looks something like this. The P orbital looks something like this. The d orbital, I think it looked something like this, and then we have one that looks like two number 8s or something like this. Yes. So if you go on to study chemistry, yeah, Chem 1 or Chem 2, just like we're doing Phys 1 and Phys 2, you will learn that in chemistry, this is actually physics بس مال الكيمياء حرامية شوية. إنزين. This is what we learn in quantum mechanics later on if you do advanced physics. You will learn of principal numbers called N, L, and M. Otherwise, in high school, they taught you this N is shell number, and they taught you that L was orbital. So 1, 2, 3, 4. S, P, D, F, and you probably never did M at that point. Yeah, but you probably asked your instructor in high school, okay, why can S take 2 and why can't P take 6, so that second orbital can take 8, and then why is this 18? Why is this able to take 2 and this 6? And then why is this able to take 10 and so on and so forth? You probably asked them this question and they either told you, which I would be very happy, or they might have told you it's too complicated, you will learn it later. The reason why they can take more and more is because of this M. The M gives them different energies. Now, what is that middle letter there? This middle letter. What does it remind you of? Have you made the connection yet? The orbitals are determined by the amount of angular momentum available to these subatomic particles. Okay, so this is something to look forward to, that what we're doing in this course isn't just isn't just useless. It actually has a lot of applications later on in very advanced courses. Cool. So this is it for today. See you inshallah on well, some of you Sunday, the others on Monday, inshallah.